Dear all, this is a video on in AC circuits. Okay. Hello everybody. So let us continue. Dear all, today I am going to make this video, that is video number 30, on your electromagnetic waves. So this is your chapter number 32. So let us start with the subchapter 31.1, sorry, 32.1. And this is your Maxwell's equation and electromagnetic waves. Okay, so why we have written Maxwell's equation, even though we have covered it in the last videos. In the last chapter we have also covered about Maxwell's equation, but still then we require a lot of application of this Maxwell's equation in your electromagnetic waves. That is why we have to revisit this Maxwell's equation. Now before that, let us try to understand what is this electromagnetic waves. Now, as the name suggests, your electromagnetic waves consist of two terms. One is your electro and the other one is magnetic. That means, as the name suggests, it is going to have both the electric field and the magnetic field. That means any wave which is having both electrical field and a magnetic field are known as electromagnetic waves. Now at this point of time, it may seems to be a little bit confusing, but in a long course I will explain, and moreover it is quite a easy one, even though it looks a little bit complicated, but it is a very easy one, and I will try my best to make you understand it in detail. Now before that, let me tell you what are the applications of electromagnetic waves. So everything that you see is because of light. So light is a very beautiful example of your electromagnetic waves. Other examples of electromagnetic or commonly used examples of electromagnetic waves includes your radio and television signals. So radio and your television signals, your mobile signals, all these are nothing but your electromagnetic waves. Similarly, your light waves or light rays are also electromagnetic waves. Light rays, your X-rays, your infrared light, your ultraviolet light, all these are nothing but your electromagnetic waves. Now, what is this electromagnetic waves? As I told you that usually what happens, suppose in a pond I will drop a stone. Suppose this is a pond, and in this pond there is water, and I will throw, the water is absolutely stagnant, let us say. So if I drop a stone, what is going to happen? Water or the energy of impact is going to be transmitted in all directions, and it is going to make waves. Now, in the same way, your electromagnetic waves can be defined as a method of transmitting energy. Which type of energy? Electrical energy. But unlike your throwing of a stone into the pond water and the water exhibiting your waves, example of mechanical wave is your sound signals. That means when I am talking to you, actually there is a mechanical motion, and this is how the energy from my voice is going to be transmitted through the air into your ear, and thereby it is going to vibrate your eardrum, and you are going to listen to what I am saying. But unlike that, your electromagnetic wave is not a mechanical wave. It is a electromagnetic wave. So be careful, because mechanical waves and electromagnetic waves are two different things. Now, obviously, these sorry, these electromagnetic waves, no doubt, are going to have the same basic properties of any wave. For example, your velocity will be equal to lambda into f. So all these things are same for both of these waves, because after all, your electromagnetic wave is nothing but a wave. But unlike a mechanical wave, your electromagnetic wave is a little bit different. So how it is different? So the first and the most important difference is that in mechanical waves, you require a medium for transmission of these waves or energy. Whereas in case of your electromagnetic waves, you don't require any medium. If there is no medium, or there is vacuum, or you can say there is free space or air. So in all these things, obviously air is a medium, it doesn't matter. So it actually doesn't require any medium or any particle to move. That means in space, the cosmic rays or the sunlight that is coming, or the stellar waveforms that are coming in the form of radio signals, all of them doesn't require any medium, because in the vacuum space, it is considered to be vacuum. There is no matter in the space. So even if there is no matter, obviously these electromagnetic waves can still pass through them. Similarly, your electromagnetic waves can also pass through your material or medium. For example, your flow of electricity is also electromagnetic wave, but the only difference is that instead of traveling in a free space, it is actually propagating through a conductor. So this is also an example of your electromagnetic, but it is not known as wave because there is a medium, that is your metallic conductors. So, but in case of mechanical waves, you require a medium. For example, suppose in between you and me, there is vacuum, and if I speak out, you cannot hear anything, because my voice signals cannot pass through vacuum. So it requires a medium. But unlike that, your electromagnetic waves, it doesn't require a medium. And one of the most brightest example is that the light waves coming from the sun. The sun is located in the space, and in the space there is vacuum, or it is known as free space. And there is no medium, but still then you are receiving sunlight. Similarly, the radio signals emitted from stars or different galaxies, they are also transmitted through this space, and the space doesn't contain any medium, but still then you can receive it on the Earth's surface. So this is one major difference. Now this is a very simple difference, but what is the major difference? Let us try to look. For that, let us revisit the word electromagnetic waves. That means such a type of wave is actually going to have both electric and magnetic field. That means suppose a mechanical wave can be plotted very simply as a wave like this. So what is happening in the mechanical wave? You have on the y-axis you have the magnitude, let us say x. On the y-axis you have the magnitude, and on the x-axis you have the time. So this is how the magnitude of the wave, mechanical wave, is varying with respect to time. So it is a one-dimensional wave. But your electromagnetic waves are not like that. How it is going to look like? Now, in case of electromagnetic wave, and look over here, this is varying in 2D and it is traveling in this direction. The direction in which the mechanical wave is traveling, or any wave is traveling, is known as the direction of propagation. Now just have a look at your electromagnetic wave. Let us say this is your x-axis, this is your z-axis, and this is your y-axis. So what happens? Your electromagnetic waves contains both electric field and magnetic field, and both of them are varying with respect to time. That means this is not a static electric field, it is a dynamic or a time varying electric field. Similarly, your magnetic field is also time varying magnetic field. So as you can see in this way, I will show you that if this one is your electric field wave, electric field, now you can see this electric field is traveling and in the direction of x, because x is the direction of propagation, and its magnitude is actually varying in the direction of y. So let us say this is your electromagnetic wave. This is your electric field. Now, when I am talking about electromagnetic wave, obviously what happens, as I told you, both electric and magnetic field are present. So I have depicted the time varying electric field over here. Now, what about the magnetic field? Obviously, the magnetic field will also be varying with respect to time like this. Now, your magnetic field, as you can see, this is not the direction. As you can see, it is actually varying with respect to time, but its magnitude is varying along the direction of z-axis. Whereas for that of your electric field, it is actually varying in the direction, or the magnitude of the electric field is varying along the y-axis. So as you can see that in this one is your electric field, and this one is your magnetic field. So you can see that this electric field is, as I told you, that your electromagnetic waves consists of electric field, time varying electric field, and time varying magnetic field. Now in this figure you can also see I have depicted an electromagnetic wave, and it looks like this, exactly like this. So here what you are seeing, that this electric field is changing with respect to time. That means it is a time varying electric field. And the magnitude of this electric field is along the y-axis, or I can say the electric field is along the x-y plane. Whereas just have a look at the magnetic field. The magnetic field is changing its magnitude with respect to time in along the z-axis, or I can say your magnetic field is actually in the xz plane. So electric field was in the y-t plane, or y-x plane, whereas your magnetic field is along z-x plane. Now in the x-axis I have depicted the time, let us say t. So in this way I can also write that your electric field is varying as a function. I can write it as y comma t, because its magnitude is along the y-axis and it is propagating in the direction of x-axis, and over there, since it is traveling, therefore I have taken the time. Similarly, your b vector is having this function, that is b vector is a function of z comma t, because your b vector is also varying with respect to time, and moreover its magnitude is along the direction of z, whereas the direction of its propagation is along the x-axis, where I have represented it as the time axis. So this is the basic idea of learned is the surface integral of E vector dot dA vector is equal to Q enclosed by epsilon 0. Okay, so this was known as Gauss law for electrostatic field. Now over here your electric field is not changing with respect to time. That means if I will plot a graph between your time axis and your electric field axis, it is going to be constant like this. So this is a static electric field, whereas in the previous case I was talking, so the electric field was changing in this manner, so I can say that it is a time varying electric field. Time varying electric field. Okay. It doesn't matter whether it is varying sinusoidally or whether it is changing in the form of square waves or whether it is in the form of sawtooth wave. It doesn't matter. So if it is changing, or if the magnitude is changing with respect to time, it is known as a time varying electric field. So the first Maxwell's equation that we came across is the closed surface integral of E vector dot ds vector is equal to q enclosed by epsilon 0. So this is the first Gauss law, and this Gauss law is only applicable for static electric field, and therefore this is only applicable to electrostatic fields. The second law is known as closed surface integral of B vector dot dA vector is equal to 0. Now this thing we have studied when we are talking about magnetostatic. So what does this equation shows? This equation shows that the magnetic field, the total surface integral of B vector dot dA vector is equal to 0. That means the total magnetic flux enclosed by a closed surface is 0. In this case, this was Gauss law for electric field, and it says that the closed surface integral of E vector is equal to the total charge enclosed by epsilon 0, and it is equal to your total flux coming out of the closed surface, electric flux coming out of the closed surface. Now what does this equation shows? This equation shows the total flux, magnetic flux coming out of a closed surface is equal to 0, and this is known as Gauss law for magnetic field, or rather I will say magnetostatic field, because in this case also this B vector is not changing with respect to time. It is a static magnetic field. Now the third equation, that is your Ampere's law, it says that the closed line integral of B vector dot dl vector is equal to mu naught times of IC, that is your conduction current, plus your ID. And what was ID? ID was equal to epsilon 0 d phi E by dt. So this we have derived that this is known as your displacement current. So Ampere's law says that B vector dot dl vector is equal to mu naught times of IC plus epsilon 0 d phi E by dt. Now let us have a closer look at this equation. So what is IC? IC is known as the conduction current. Now what is conduction current? I have told you there are three types of current: convection current, conduction current, and displacement current. Now what is this IC? IC is the conduction current. That means all those current that arises because of the flow of charge through a ohmic conductor. Now, obviously, when we were talking about electromagnetic waves, we are actually not talking about the conductor, rather we are talking about vacuum or free space. So, obviously, in free space, and free space is not an ohmic conductor, and therefore I can say that your IC is equal to 0 in free space. In free space or vacuum, your IC, that is your conduction current, is equal to 0. So this equation can be a little bit modified and written as mu naught times epsilon naught d phi E by dt, or this I can write it as dE vector A vector divided by dt, because your phi E is nothing but dE A by dt. Now this is known as your Ampere's law. And the last Maxwell's equation says the closed line integral of E vector dot dl vector is equal to minus d phi B by dt. And this we can also write it as minus d BA by dt, because your magnetic flux is nothing but the magnetic field into the area passing through it. Now, so these are the two equations, and let us try to analyze these two equations in detail. So the first equation, the third equation is your Ampere's law, and it says the closed line integral of B vector dot dl vector is equal to mu naught times epsilon naught dEA by dt. Okay. So just have a, okay, this is the equation, and the next equation, that is your Faraday's law, says the closed line integral of E vector dot dl vector is equal to minus d phi b, that is nothing but ba by dt. Okay, so B is a vector, A is a vector, E is a vector, and this E is also, A is also a vector. Now, just have a closer look at this. Now, obviously at this, just have a look at this equation. Now, in the previous equation, you saw that E vector dot dA vector is equal to Q enclosed by epsilon 0. So, if there is an electric field over here, there is no magnetic field on the right hand side of this equation. Similarly, for the second equation, just have a closer look. You have a magnetic field on the left hand side, but there is no electric field on the right hand side. Now, these two, as I told you, are your static fields. These are the equations from static field. This is the equation from your electrostatic field. This is the equation we drew from your magnetostatic field. Now, let us have a closer look over here. Now, these two equations we only learned when we were dealing with, so these two equations we learned when we were dealing with time varying fields, time varying fields. Okay, now look over here. Now, as you can see, in this particular case, dE by dt. What is dE by dt? It clearly shows that your electric field is changing with respect to time. So whenever I am writing dx by dt, it actually means what? That x is varying with respect to time. So over here we have that closed line integral of B vector dot dl vector is equal to mu naught epsilon naught d phi E by dt, and phi is nothing but Ea. So in this particular equation, as you can see, that it is changing, your dE is changing with respect to time. Now, when an electric field is changing with respect to time, there is a magnetic field associated. Similarly, look at this equation. In this equation, you can see, please hold. Okay, so in this equation, you can see that your B is changing with respect to time. So when B is changing with respect to time, it is not a magnetostatic field, rather we call it as a time varying magnetic field. So whenever there is a time varying magnetic field, there is a generation of electric field. That means whenever I am talking about time varying fields, if one field is present, the other field is bound to be generated. That means suppose there is a change in the electric field, then obviously there will be a generation of magnetic field and vice versa. So whenever, just remember, this is a very important point. Whenever your electric field is changing with respect to time, or there is a time varying electric field, there will be an associated magnetic field. Similarly, if there is a time varying magnetic field, it is bound to create a time varying electric field. So these two things are the basis of your electromagnetic waves. So in other words, I can say when an electric and magnetic fields are static, that is when they do not vary with respect to time, your E vector and B vector are independent to each other. So the most important thing, just a minute. The most important thing that we must remember throughout our life is that when your electric field and magnetic field are static, they are independent of each other. They are independent of each other. So this is a very important thing. Okay. So there was some shaking of my hand. That's why I came over to this place to record. Okay. So as I told you beforehand that whenever your E vector and B vector are static, or your E vector is time invariant, E vector or B vector are time invariant, That means they are static. They are not changing their magnitude with respect to time. In that case, your E vector and B vector are absolutely independent of each other. Absolutely independent of each other. What is the proof? The proof is the previous Maxwell's equation. Your closed surface integral B vector dot dA vector is equal to 0. Here B vector is static, that is it is time invariant. Therefore, on the RHS side, you don't find any term regarding E vector. Similarly, the closed surface integral of E vector dot dA vector is equal to Q enclosed by epsilon 0. Over here, you have this E vector is time invariant. That means it is static in nature. Its magnitude is not changing with respect to time. And in this case, you can see on the right hand side, there is no B vector term. It clearly suggests that for a time invariant field, electric or magnetic field, or in other words, for constant magnitude of E vector and B vector, they are both independent of each other. But the moment E vector and B vector are time invariant, or in other words, E vector or B vector starts changing their magnitude with respect to time, then obviously there will be a counterpart electric field. So, as I told you, from this Maxwell's third equation, that is your B vector dot dl vector is equal to mu naught epsilon naught d phi e by dt, and as you know, E is equal to phi e is equal to a E vector dot a vector. Now in this case, as you can see that this equation can be written as mu naught epsilon naught. Let us take this a out. We have this dE vector by dt, and this is closed surface integral of B vector dot dl vector. Now in this case, as you can see, there is a term dE by dt. What is this? This is nothing but your time varying electric field. So whenever there is a time varying electric field, it generates a time varying magnetic field over here. So this B vector is actually changing with respect to time. It is not static in nature. So this is the third Maxwell's equation, which suggests that such a type of equation is responsible for generating electromagnetic waves. The fourth law, that is your Faraday's law, is closed line integral of E vector dot dl vector is equal to minus d phi b by dt. And what is phi b? It is nothing but your b into a. That is, I can write it as a db vector by dt. What does this suggest? This suggests that whenever there is a change in the magnetic field, or whenever there is a time varying magnetic field, then obviously there will be a generation of time varying electric field. And this is another important equation which leads to the generation of electromagnetic waves. So at least we concluded that whenever E vector and B vector, E vector or B vector are constant or time invariant E vector and B vector are independent. But if E vector, very important things I am telling, please be careful. If E vector and B vector are changing with respect to time or time varying, so this is time invariant. If E vector and B vector are time varying, implies E vector produces, time varying E vector produces B vector, and time varying B vector produces E vector. So, as I told you beforehand, that whenever there is an existence, simultaneous existence of both electric field and magnetic field, then it leads to electromagnetic waves. Very important thing, whenever both E vector and B vector time varying E vector and B vector are simultaneously present, it leads to electromagnetic waves. So at least we concluded that from Maxwell's two equations, from these two equations, your time varying fields is going to be generated, and this leads to the generation of electromagnetic waves. Okay, so we can say that the generation of your electromagnetic waves is because of time varying electric field or magnetic field. Now, just hold on. Now, in the next video, we'll study how the electromagnetic waves are generated, what is the electric spectrum, and further we will analyze. So with this, I am going to conclude this video. In the next video, we will start with other aspects of electromagnetic waves. Thank you. Okay, so in this video, we'll first learn how we are going to generate an electromagnetic wave. Generation of electromagnetic waves. Okay, so let us say I have a point charge, positive point charge plus Q. Now this is stationary in the space. So when it is stationary, the electric field produced because of this positive charge, point positive charge, is also stationary in nature. Similarly, if I have a negative charge, even though the directions of your electric field are in this manner, still then the electric field is stationary. So in these two cases, your electric field E vector is static. That means it is producing an electrostatic field. So we all know that whenever the electric field is static or it is not time varying, then there is no generation of electromagnetic waves. But let us say this charge, suppose let us say this charge is making a simple harmonic motion like this, okay, along this curvature. Now let us say I will put this charge over here, and let us say the charge moves in this manner. Let us say this is the equilibrium point O, this is one extreme point A, this is the other extreme point B. Now if the charge is over here and let us say it moves in this path, now while it is moving in this path, it is accelerating, and because of this it is going to gain an increasing amount of speed. So the speed is changing with respect to time. Secondly, its direction is also changing. Now let us say this charge, because of the moment of motion, it overshoots this equilibrium point and it starts moving towards this point. So in this process, it starts decelerating. Now, if it is decelerating, then obviously the velocity, the speed is also decreasing, is changing. Now at this point, it again stops and tries to move back to the equilibrium point. So in this way, as you can see that this point charge is making a simple harmonic motion. So when a point charge is making simple harmonic motion, then the electric field is time varying. So when it is time varying, obviously it is going to produce an electromagnetic waves. So this is the basic principle, and with some engineering modification, we usually design the antennas in this way so as to generate electromagnetic waves. So usually what we have an alternating source, and to this we have an antenna like this, and in positive half cycle, the electrons will start moving, or the charges, negative charges will start moving in this antenna in this direction from positive to negative. So in this way, it is going to move in this direction, and in the other half cycle, this one becomes positive and this one becomes negative. And this charge again moves in the opposite direction. So there is a to and fro motion of the charges inside this antenna. Let us say this is your antenna, not a conductor, this is an antenna. So in this way, it is going to produce a simple harmonic motion, and it is going to create your electromagnetic waves. So basically what we usually have, we have an LC circuit, and that LC circuit is energized by an external source, and it is going to develop your electromagnetic waves. Even we have also studied that when there is a coil like this, and to this coil I applied a time varying voltage, that is your sinusoidal voltage, then obviously the electric field, the magnetic field produced B is time varying over here, is time varying. Because why it is so? Because your I is going to be sinusoidal in nature, because we have applied a sinusoidal voltage. Because of this, sorry, because of this sinusoidal voltage, there is a sinusoidal current. And this sinusoidal current is responsible for producing a time varying magnetic field. And you all know that whenever there is a time varying magnetic field, it leads to the generation of an induced EMF. And this induced EMF, this induced EMF is what it is going to do? It is going to create a time varying electric field. So as you can see, there is a time varying magnetic field which is producing a time varying electric field. And when both of them, or I can say if there is a time varying magnetic field, it is leading to the formation of time varying electric field. So in this way, it is also going to create an electromagnetic wave. So basically what happens, whenever I am going to have a time varying electric field, it is going to produce a time varying magnetic field, and when I am having a time varying magnetic field, it is going to produce a time varying electric field. And in this process, it is going to generate your electromagnetic waves. Next, we will study what is your electromagnetic spectrum. What is electromagnetic spectrum? Sorry. Now, before going into electromagnetic spectrum, let me tell you, there is a very important property for this. Sorry. Before starting with the electromagnetic spectrum, let me tell you a very important formula which is related to all types of waveform, whether it is mechanical waveform or electromagnetic waveform. What is that formula? The formula says the velocity of propagation of the wave is equal to the wavelength lambda times the frequency f. So this is a very, very fundamental equation or expression related to all types of wave, irrespective whether it is a mechanical wave or your electromagnetic wave. Here B is the velocity of propagation of the wave, velocity of propagation of the wave. Lambda, okay, the unit is meter per second. Lambda is the wavelength of the wave, and obviously it is in meter. So if I am having a waveform like this, then one wavelength is equal to this much, one complete cycle. So it is measured in meters. And frequency, what is frequency? Frequency, F is known as the frequency, and frequency, the unit as you all know is hertz. Now, so this is a equation which is common to all types of waveform, whether it is mechanical or electromagnetic wave. But when we will concentrate only on electromagnetic waves, then in this case, your V is equal to C. What is C? C is the velocity of light. That is, it is a constant 3 into 10 to the power 8 meter per second in vacuum. So when, please note that when your electromagnetic wave is passing or propagating through vacuum or free space, it travels at the speed of light. And obviously, your C is also going to follow the same principle, that is, C is going to be lambda times the frequency of the electromagnetic wave. Can you all hear me?
Yes, sir.
Yes?
Yes, sir.
Okay. Yes, sir. Okay, fine. So many of you are complaining that the videos are not accessible to you. So don't
Yes,
worry
sir.
about that. I'll since I have sent it from my official email ID, that is why you are having problem. So kindly somebody please give me your mail ID so that on the WhatsApp group you send someone's mail ID. I'll be sending it from my personal mail ID. Okay.
Okay, sir.
Uh, right now, okay, let me do it right now because all these are quite important for you all.
Sir, it is showing access denied.
Yeah, I know that and because I have sent it from my official email ID. That is why you are having problem. Okay, don't worry about that. I'll be sending it from my personal mail ID. Right now itself I'll be sending it. Don't worry. Somebody please tell me someone's email ID. Just WhatsApp it. No, I haven't received it till now. Oh, meet chat. Okay. But I have not loaded that one. Oh, meet chat. Okay, okay. Let's circulate it among your friends. Just a minute. I'll be just dispatching it. This is going going to take some time. Okay, we'll stop the video over here and we'll start with our class.
Sir, if you give access, then we can take now.
Pardon, I cannot hear you.
Sir, if you give access to the video, then we can take now.
No, actually, I have also received one mail from the section coordinator regarding both the sections that I should not be sending it. So that's why I am trying to send you over my personal email ID. Okay. In that way, there will be no hustle officially.
Okay, sir.
Please wait for some time for the class to start.
Okay, done. Great. Is the slide visible to you? Okay. So last class we talked about the different types of circuits. We talked how this AC is going to behave in case of purely resistive circuit, purely inductive circuit, and purely capacitive circuit. And we learned what is going to be the voltage expression for the voltage across each of these pure elements. We studied about how they are going to differ in their phase, or how this phase difference is going to be. We also learned how the phasor diagrams are going to be. Along with that, we learned about the waveforms. So we have already covered all these things, and with that also we covered about this variation in the resistance, capacitive reactance, and inductive reactance with the variation in applied frequency. So till by far we have completed up to this much. So now let us just have a recap of what we actually have covered by now. So as you can see in this table over here, this column is representing all the parameters that we are going to discuss, and these columns are going to indicate the different circuit elements that we were talking about. And as you can see, the first parameter is current applied, and in each of these, the current applied is given by the expression Im cos omega t. Secondly, in the voltage drop also, I wrote something like VR is equal to Vrm cos omega t plus phi. Over here also, I have written it in exactly the same form, that is VL is equal to VLm cos omega t plus phi, and followed by Vc equal to Vcm cos omega t plus phi. Now let us see for ourselves what is going to be the values of this phi in each of these cases. So as you know that phi is nothing but your phase difference. So obviously in case of a purely resistive circuit, the phase difference is going to be 0 degree. So this equation can be rewritten as VR is equal to VRM cos omega t. That's all. Secondly, if we talk about power factor, and I know that you know what is power factor, that is nothing but the cosine of the phase difference between the voltage signal and the current signal. So in terms of your circuit, you can write it as R by Z. Forget about this Z, till now I haven't explained it, though you have some idea about this Z. So forget about that. So cos phi in case of a, or power factor in case of a purely resistive circuit is always going to be 1. Why? Because cos of 0 degree is equal to 1. Now let us throw our light on this purely inductive circuit. So in this case, your phase difference is plus 90 degree. So you can write the voltage drop equation as VL is equal to VLM cos omega t plus 90 degree. And the cos of 90 degree is equal to 0. That is why the power factor of a purely inductive circuit is going to be equal to 0. So in this case, that in the remark we have written that voltage drop across the inductor always leads the current passing through it by 90 degrees. So this is the most important remark. Next, if we will discuss about this purely capacitive circuit, over there your phi, that is the phase difference between this voltage signal and this current signal, is going to be minus 90 degree. Again, your power factor is equal to cos of minus 90 degree, that is equal to 0. So it is written as 0 over here. Lastly, regarding the remark, it is the voltage drop across the pure capacitor which is going to lag the current passing through the pure capacitor by 90 degree. So this is all what we have studied by now. Now let us move on to a mixed circuit. So till now we have been talking about purely resistive circuit, purely inductive circuit and purely capacitive circuit. But the truth is that in our day-to-day electrical life, we always come across a combination of different types of elements. So naturally, if you will open up any electronic gadget, you will see that there are a lot of resistors, lot of inductors, capacitors. You will also find microcontrollers. You will find relays. Number of stuffs are present. But forget about you will also find diodes, transistors, op-amps. Then you may also find thyristor. So there are multiple number of equipments that are present on any electrical or electronic circuit. But whatever be the case, just remember that out of all those stuff that you are seeing on a circuit board or in a motherboard, RLC, they are the most important and they are the prime elements of any circuit. So now let us talk about a simple mixed circuit. That is, we will talk about a series RLC circuit. Now already we have discussed it in the lab class, but now in a very elaborate manner we will study about this series RLC circuit. Now obviously if series is existing, then parallel RLC circuit also exists, and parallel RLC circuits are also used, but your course has limited your course syllabus to only series RLC circuit. So naturally over here, as you can see in the slide, that I have a pure resistance connected to a pure inductor connected to a pure capacitor, and all of the connections are in series, and this entire series combination is connected across a voltage source, which is a sinusoidal voltage source. Now in the same way that we have treated all those pure elements, we will also find the derivation, we will also carry out the calculations in exactly the same manner. Now over here, let us say that I am having this series combination of all the elements which is connected across a sinusoidal voltage source. Now since it is a closed circuit and moreover it is a series circuit, the same alternating current is going to flow through all of these circuit elements. Now obviously if the current is going to flow through all of them, obviously there will be voltage drops across this resistance. So that voltage drop, let us say, is VR. Similarly, there will be voltage drop across the pure inductor. Let us say that voltage drop is VL. And ultimately there will also be voltage drop across the pure capacitor, and let us say that voltage drop is equal to VC. Now as I have told you that unlike your algebraic or DC circuit where you simply add all the voltage drops in that KVL you add all the voltage drops algebraically. But remember, this is a purely AC circuit, and obviously in case of AC circuit, you cannot add the voltage drops directly in an algebraic manner. So what you have to do, you have to add them phagorytically, or rather I will say, you have to add all the voltage drops vectorially. So you know vector addition and your algebraic addition, both of them are completely different from each other. So naturally, since Phasor algebra is also going to follow your vector algebra, so naturally we will add all these voltage drops phagorytically. Rather, I will say we will add them in a phasor diagram. So that is the best or easiest possible way by which we can add the vectors in a very simple manner using less energy and less complexity and less time. So finally, let me tell you about the circuit. So as I told you, we are having a voltage source which is giving out a voltage of V. A current I is flowing through this entire circuit. The voltage drops are VR, VL and VC. So ultimately we can say the total current that is passing through this entire circuit, series circuit, is given by I equal to Im cos omega t. Now what about this V? V is equal to Vm cos omega t plus phi. Now obviously I cannot define or I cannot write anything about this phi right now. Why is it so? Because this is a combination of all the three elements. So this is a circuit, VR will be in phase, whereas your VL and VC will be out of phase by 90 degree. So in that case, we cannot simply predict what will be the value of this phi. So ultimately we will see how we are going to find the value of this phi. Secondly, we are going to introduce one concept, that is your impedance, the concept of series impedance. So all this thing let us try to find out. And over here, let me tell you one thing. When I am going to draw the phasor diagram over here, I'll only be using the RMS value. Okay, so you know what is RMS value. So if VR is given by, let us say VMR cos omega t, so that VRM by root 2 is going to give you a VR, that is capital VR. RMS values are always written in capital letters, whereas your instantaneous or time varying parameters like your instantaneous voltage or your instantaneous current, all of them are written in small letters. So let us try to find out the concept of impedance, and also let us try to find out the expression for this phi by using the phasor diagram. There are obviously theoretical method is equally applicable. You can also find it out in that way, but explaining you in terms of phasor diagram will be a easier one. And moreover, your course is also asking us to teach you in phasorical form. So as you can see over here, these are the two phasor diagrams. Now why two cases are over here? Because by far till now I don't know whether my XL is greater than XC or XC is greater than XL. Because as you will see afterwards that the value of this phi is actually going to depend on whose value is higher, whether XL is greater than XC or XC is greater than XL. Okay, so let us try to find out. So over here, I have tried to draw the phasor diagram of the RLC series circuit. So over here, there are two cases. The first case is when your XL is greater than XC. The second case is when XC is greater than XL. Now, both the circuit and phasor diagrams are quite easy to understand. So as you can see, the first case let us discuss. So as you can see over here that I am having this IRMS, and I have taken this IRMS as the reference quantity. So since I have taken it as the reference, therefore I have drawn it horizontally in this manner. So obviously your VR, that is the RMS voltage drop across the pure resistor, will be in phase with this I. That is the reason why both of them have been drawn overlapping each other, because the angle difference between them is equal to 0. Next comes your VL. So as you can see that we know that your VL always leads the current by 90 degree. So since it is a pure inductor, the voltage, RMS voltage drop across the pure inductor obviously is going to lead the current by 90 degree. Now, since we are adding each of them, so you know that in case of vectors, if you are going to add them, so you have to add from head to toe, head to toe. In this manner, you are actually going to add. The same principle is also applied over here in case of phasor diagram. So this from here to here, it is your VR. Okay. From this head, I have dropped this VL in this direction, making an angle of 90 degree. Why? Because your VR is coinciding or overlapping this I, because they are having a phase difference of 0 degree. So since 90 degree means, so I should have drawn it over here, but since we are adding, therefore we have added it in this manner. Next, what about this BC? So BC obviously is going to be out of phase from this I by minus 90 degree. So naturally this BC in blue color should have been dropped over here. But the thing is that since we are adding them, therefore from this head, the toe will be there for this BC, and I have drawn it in this manner. So from here to this point, it is your VL, and from here to here, it is your VC. So ultimately, as you can see, that I have added all of these vectors considering XL to be greater than XC. So this is your VR, followed by this is your VL, and from this tip, I have dropped VC in this direction. So when three of these vectors are added, it will result in the total voltage drop across them. Now, what is the total voltage drop across them? It is nothing but it is equal to the RMS value of the voltage source. So naturally, in this case, your V, capital V, without any subscript, is actually indicating the RMS value of the voltage source. So how we are going to find that? From the starting point till the end point, we will join, and this vector is actually going to represent the voltage source, the source voltage RMS value. So in this way, we have found the value of this V. Now over here, as you can see, that XL is greater than XC. So you can see the magnitude. So this is the magnitude of your VL, and this is the magnitude of VC. So naturally, what is XL? XL is nothing but, what is VL? VL is nothing but XL into I. So naturally, this one is greater than that of your VC. So in this way, when we will join these two from the starting point till the end point, we are actually getting the value of the VRMS for the source. So this is the total voltage drop across all the three elements, and this is written in terms of RMS values. Now, how we will define the phi? Because I have told you that phi is nothing but the phase difference between the applied voltage and the final current flowing through the circuit. So the current flowing through the circuit is I, and the total voltage drop across the circuit or applied voltage drop across the entire circuit is V. So as you can see, they are inclined to each other by an angle of phi. And moreover, this angle, because I have taken this I as the reference, so you can see the angle is in anti-clockwise direction. So naturally, in this case, your phi is going to be positive. So in other words, I can say this entire circuit is actually a net inductive circuit. Please note it, it is a net inductive circuit. So naturally, the value of the inductor is going to, or rather I will say, the value of your XL is going to play a major role than that of the value of XC. So in this way, we can draw the phasor diagram, and from there we can evaluate what is the value of your phi. Now let us mathematically try to find out the value of phi. So over here, now this is what we have drawn by means of phasor diagram. Let us try to understand it in a theoretical manner. So theoretical manner means your V. Now you can see V is equal to VR square plus VL minus VC whole square. Forget about this square. This is a extra bracket I have drawn. So no need of looking at this. So your VR square plus VL minus VC square root over is actually going to give you the total voltage drop across all the circuit elements, or it is the voltage drop that is applied across the circuit elements. Now there is nothing difficult about this, because as you can see, if this one is V and this one is your this portion is your VL minus VC, and both of them are 90 degree to each other. Just apply Pythagoras theorem, you are going to get the value of V theoretically. Okay, so up till now I hope everybody have understood. This is not a very big deal. Now let us define this V. Now V is nothing but the voltage drop across the total circuit or the total RLC series circuit. Let us say I will introduce one term, that is Z. And what is this Z? This Z is known as the impedance of the series RLC circuit. Now what is this Z? This Z is nothing but an opposition, combination of all the oppositions. So I have told you what are the oppositions: resistive opposition. Then we studied about the inductive reactance, that is also a opposition, and ultimately we studied about the capacitive reactance, that is again a opposition. So when all of these oppositions are combined together, it is nothing but known as the impedance of the circuit. Okay, so obviously the voltage drop is equal to I times the total or the net opposition, because when in case of DC you have studied that V is equal to IR. So IR and R over here is the opposition offered by the pure resistive circuit. Similarly, your V in case of a pure inductor is given by IXL. Now XL is again opposition offered to the flow of current. So this XL plus this R plus your XC, all of them combined together are actually known as the net impedance of the circuit. So your V is nothing but or the voltage drop across all the circuit elements, or in other words, the voltage applied across all the circuit elements, that is V is equal to I times your impedance, net impedance of the circuit. So for in place of this V I have written as IZ. Now this is equal to, now let us do one thing, in place of VR let us write it as IR. So it is, since it is VR square, it is I square R square. In place of this VL, I will write IXL minus IXC. C should have been subscript over here. Okay. So if I square this as a whole, then I will take this I square outside, and what I am left is XL minus XC whole square. Now let us do one thing. Let us take this I and this I outside this root over sign. So if I do that, your I will be over here. So I will get cancelled out, and ultimately what I am left with is Z is equal to R square plus XL minus XC whole square root over. Okay. Now remember, when we will study about these two things, we will see that since it is a square term, it doesn't matter which one is greater or which one is lower. The opposition offered is going to be the total addition, vectorial addition of all the oppositions. Now let us try to define what is the phase angle difference mathematically. So as you can see, what is this phi? This phi is nothing but tan inverse of this element, this much portion divided by this total one. So what is this? This is nothing but your XL minus XC divided by R. So ultimately we come to the conclusion that your phi is equal to tan inverse XL minus XC by R. But remember over here, if the circuit is having an inductive reactance more than that of your capacitive reactance, your phi is going to be positive. Now that is quite evident, because here you saw that your phi is directed in the anticlockwise direction, and therefore it is positive over here. Is there any doubt? Anyone with any sort of doubt? Okay, fine. Now let us throw some light on the second part, or in the case 2, where we have this XL to be greater than that of your XC. So let us see what is going to happen. Same thing, the current I is taken as the reference. VR is on the same direction because there is no phase difference. Now here we have this VL. Now this VL is less than VC. Why? Because your VL is this much. So it is starting from here, ending at this point. Whereas your VC is actually starting from the tip or head of the VL and it is terminating over here. So as you can see, it is quite evident that your VC is much greater than that of your VL. So the net voltage drop will be this one. So this portion is nothing but your VC minus VL. Okay, if this is the case, let us now write down the equation for this V. Now, obviously, theoretically, we have found our V because V is nothing but it will start from the starting point and end at the ending point. So, your V is equal to VR square plus VC minus VL whole square. Now, in the same way, I will write this VR in terms of IR. So, it is coming as I square R square. And for this one, it is going to be I square XC minus XL whole square. L should have been subscript over here. Now, if I take this I square common out of this bracket, it is again going to be I. So this I and this I will get cancelled out, and ultimately what I am going to get is Z is equal to R square plus XC minus XL square. Now just have a look at this case. Now in both the cases, these second terms are squared terms. So if you interchange their position, then also it doesn't matter because it is a square term. It will not be zero. No, it will not be negative. But the most important thing is that of this phi. So over here, as I have already told you, what is this phi? This phi is nothing but this distance, tan inverse of this distance divided by this distance. So naturally, this total distance is, let us say, is equal to VR, or rather I will say R. So over here it is nothing but XC minus XL. So if this is the case, then obviously your phi is going to be tan inverse XC minus XL. Now if this is the case, when the net impedance of this circuit is capacitive in nature, then obviously the voltage is lagging behind the current by an angle of phi. And as you can see, phi is in the clockwise direction. That means this phi is negative. So always remember that this is a rule which must be remembered forever. What is that? If it is a net, I am talking about net, not pure. I am talking about a net inductive circuit, then your phi is considered positive. And if the circuit is a net capacitive circuit, then your phi is considered as negative. So this is the most important thing, because you may find questions where you will be asked that there is an unknown element in the unknown element connected across a AC supply, sinusoidal AC supply, and the value of this phi is found to be minus 21 degree. So predict what type of circuit it is. So you have to write it that it is going to be a net capacitive circuit, not a pure capacitive circuit. Why it is so? Because it is minus 21 degree. If it would have been minus 90 degree, then obviously you could have written it as a purely capacitive circuit. But since it is less than a minus 90 degree, so you have to write, it is greater than a minus 90 degree. So you have to write that it is a net capacitive circuit. So over here, as you can see, I have already defined Z is the impedance of the circuit. Please remember, there are three things: resistance, inductive reactance, capacitive reactance, and your impedance of the circuit. And all of them are nothing but opposition offered to the flow of current. And therefore, all of them are going to have their unit in ohms. Resistance, inductive reactance, and capacitive reactance, all of these are actually opposition, but the thing is that their way of opposing the flow of current is different. In case of resistance, it is because of the friction between the current carrying charges that you are getting a resistance. In case of inductor, the XL is also an opposition, but how it is opposing? It is because of the induced EMF that it is opposing the flow of current, and because you know about the Lenz's law. Similarly, in case of capacitor, why it is having a XC. Now XC is again an opposition to the flow of current. And what is the difference? The only difference is that XL is going to oppose the change in the current. It is because when the capacitor is getting a current voltage, it is actually building up an electric field, and this electric field is actually producing a voltage across it. Now this voltage is actually opposing the main cause of it, that is the applied voltage, and thereby it is opposing the current. So in all these cases, whether it is R or whether it is XL or whether it is XC, they are nothing but opposition to the flow of current. The only difference is that the way they start opposing the current. Resistance, I told you, it is because of the friction between the charges or current carrying charge carriers. In case of inductor, it is the induced voltage and all this thing. So please remember all the differences between them. Their nature is same, but their way of opposing is different. Okay, now let us try to study or throw some more light on this impedance and about this phase angle. So by now we have studied that what is impedance. Impedance is nothing but the net opposition offered to AC circuits. So the first point is very important. Just have a look. The first point is quite important. In case of DC, your V is equal to IR, whereas in case of AC circuit, your V is written as IZ. Okay. Now, Z in an AC circuit plays the same role as that of R in DC circuit. So just as DC circuit opposes the flow of current, in case of DC circuit, in case of AC circuit, it is your impedance that opposes the flow of current. So obviously, when you will go to the next semester, you will study a paper on circuit theory. Over there, you will see that in case of DC circuit, the current will always try to flow through the least resistant path. It is a common thing. So wherever the resistance is less, people used to travel in that way. Suppose there are two ways, parallel roads. In one, there is a lot of traffic. In the other one, there is sparse traffic. But both of them are having the equal dimension, that is length, breadth, everything. So naturally, you will prefer the less traveled or less trafficked road. It is because it offers you less opposition. Similarly, in case of your AC circuit, it is in place of the R, we will say it is Z. And similarly to that of your resistive circuit in DC, your AC current will always try to follow the path of least impedance. So the one which is having less impedance, in that path, maximum amount of current is going to flow. So this is all about your impedance. Now let us try to represent impedance in a little bit different manner. So as I told you that in case of DC circuit, your R can be written as V by R. Okay. So similarly, in case of your AC circuit, your Z can be written as V by I. So in case of your AC circuit, it can be written as V by I. Now, but still there is some sort of differences between this R and Z. Wow, what is the difference? Now, R is a scalar quantity, whereas Z is a phasor quantity. Okay, it's somewhat a phasor quantity. Now, why we don't usually tell that the Z is a phasor quantity? It is because phasor by phasor is not defined. But still then, it is having a lot of properties similar to that of your phasor quantities. Okay, just look over here. I have written it in the same way. Z is also a phasor quantity like AC, voltage and current, but it is not a usual phasor. Okay. Now, as I told you that Z can also be written as V by T, so instantaneous voltage by instantaneous current, or it is same as that of maximum voltage by maximum current. It is also same as VRMS by IRMS. But whatever be the case, this is the actual means relationship which you should remember, that Z is equal to R square plus XL minus XC whole square, or XC minus XL whole square root over. Doesn't matter because this is a square term. Now, obviously, these things are actually not required, but let us forget about this. Let us not discuss all these things because these are out of your course, but this is the best way to represent and do the calculations. So maybe in circuit theory, you will study all this thing. Okay. Now, as I told you that your phasor is actually somewhat a phasor quantity. So if it is a phasor quantity, then it also must be having some angle relationship. So let us try to find out the angle relationship. Now, the magnitude of this z is written as r square plus xl square minus xc square whole square root over. Now, the angle part can be written as tan inverse of xl minus xc by r. The similar manner you can also write it. Doesn't matter anyway. Now let us discuss about the power in alternating circuits. So by now we have discussed about the different forms of AC. So next we studied about the phasor diagram. Next we studied how the AC is going to behave in different types of circuit: purely resistive, purely inductive, purely capacitive, and a series RLC circuit. Next we studied about this impedance, and the last portion, or just one before the last portion, is power in alternating currents. So after this we'll study about this resonance, and with this our relationship is somewhat going to end. Okay, so this is my last class with you all. Okay, just have a look. Power in alternating circuits. Okay, now we have already discussed about how we are calculating power in case of DC circuit. Very simple. In case of DC circuit, the power is given by V into I. Okay, now let us try to understand, or let us try to find out what is going to be the expression in case of an alternating circuit. Okay, so as you can see, power is nothing but the product of V into I. So there, as I told you, if there are three types of voltage or current, like instantaneous value, maximum value, RMS value. Similarly, we also have power, instantaneous power and average power. Average power is nothing but the product of the RMS power. Okay, or it is the RMS power. Now, instantaneous power. So instantaneous power PT is equal to instantaneous voltage multiplied with instantaneous current, as simple as that. But instantaneous values are not of importance or use to us. I have already told you, we never ever use instantaneous voltage or instantaneous current. It is only meant for our calculations and other stuff. Whereas actually we make use of this RMS voltage and RMS current. Okay, but we must understand that your instantaneous power is equal to Vt into It. That is your instantaneous voltage into instantaneous current. But the power that we are actually concerned is known as the average power of the circuit. Okay. Now average power. So what is that? That is, let us designate it by capital P. So average power is the power consumed over a period of time. So how to find that? That is nothing but Pt dt integration from 0 to t 1 by t. This is the average power. It is known as average, means I have to divide it over the entire time period. So if that is the case, then let us write it down and you will see. Please go through these derivations, quite easy derivations. I'm not, because time is running out, I cannot afford to tell each and every detail. So just go through it. You can see that in place of Vt, I have put Vm cos omega t plus phi, because I don't know what exactly which type of circuit is actually consuming the power. That is why in a very generalized manner, I wrote that Vt is given by Vm cos omega t plus phi multiplied with It. Now what is It? It is Im cos omega t. So if when we will put everything in this equation, the final equation turns out to be this much. So Vm Im by t integration from 0 to t cos omega t cos phi minus sin omega t sin phi. What is this? This is because I have expanded this cos term, cos a plus cos whole into a plus b. That is nothing but cos a cos b minus sin a sin b. So exactly that thing is applied over here. And ultimately, as usual, the cos omega t terms remains over here, so it is over here, dt. Now I have to do the integration part, but before that, let us simplify this equation. So if I simplify this equation, let us bring this cos omega t in between into the bracket. So over here, I will get cos square omega t cos phi dt minus Vm Im by t integration from 0 to t sine omega t sine phi cos omega t. Now this term is going to be 0 because in this is a cyclic function, and when you will integrate it from 0 to t, it results in a 0. So ultimately your p becomes Vm Im by t integration from 0 to t. Now in place of cos square, I have just replaced it by means of this term 1 plus cos 2 omega t by 2. Cos phi remains as usual dt. Now therefore you have two number of terms over here. So let us do the first term. The first term is Vm Im t integration from 0 to t dt cos phi dt by 2. So the other term is cos 2 omega t. Again this one becomes 0 because this is a cyclic term. So ultimately what we are getting is Vm Im by cos phi 2. Cos phi by 2. Now 2 is nothing but root over 2 into root over 2. Now you can see that Vm by root over 2, Im by root over 2 cos phi. So what is Vm by root 2? It is nothing but Vrms. Similarly, Im by root 2 is nothing but Irms. Cos phi remains over here, cos phi remains over here. So ultimately, the power that is consumed by any type of AC circuit is given by Vrms, Irms into the power factor. Okay. So if this is the case, now let us consider about the different types of circuit. How much power a purely resistive circuit is going to consume. Obviously, in this case, you will put the equation. So your P is going to be Vrms, Irms cos phi. Now, in case of your purely resistive circuit, your phi is equal to 0. So cos phi is equal to 1. So this comes out to be P is equal to VI watt. So this is exactly the same as that of your DC circuit. Okay. Now let us consider a purely inductive circuit excited by an AC source. Now here P is equal to Vrms, Irms cos 90 degree plus 90 degree, and this total becomes 0. That means in a purely AC, purely inductive circuit, which is energized from an AC source, the power consumed by a pure inductor is actually equal to 0. Similarly, the power consumed by a pure capacitor is also going to be equal to 0. Why? Because in this case, your phi is equal to minus 90 degree, and oh sorry, I have written it as 0 degree. So let us change it. So cos of minus 90 degree is again coming to be 0. So ultimately we can say the power consumed by a purely resistive circuit is a purely capacitive circuit is again 0 watt. That means in a circuit, the power, it may be a combination of any circuit element, maybe a series RLC circuit or a parallel RLC circuit or whatever it may be. Remember that it is only the resistance which is going to consume your average power. Now obviously somebody may get confused that they are also circuit elements, they are also going to consume power. Then how is it possible? All these things are beyond my scope of this syllabus. Why? Because actually powers are of many types: active power, reactive power, apparent power. Now out of all these powers, we are only talking about active power. So remember, your average power is also known as active power, and active power is only consumed by a purely resistive circuit, not by purely inductive or capacitive circuit. So purely capacitive and inductive circuit, they actually consume reactive power, and the total Z, that is going to consume your apparent power. So all these terms are out of your syllabus, so we should not discuss about it. Any doubt over here?
No, sir.
Okay. So let us now move on to the last portion of this syllabus, or rather I will say my last class, that is resonance in alternating current circuits or AC circuits. Okay. What is this resonance? So the first time you heard about this resonance is when you are studying your 11th class mechanics paper. Over there, when you are studying about oscillations, there was a particular case where the first time you heard about resonance. So particularly since I have studied in Odia medium, I don't know about CBSE board, but usually those who have done their plus two from Odia medium, they know that in Barik Das Sharma physics book, there is a particular example that the soldiers are traveling over a hanging breeze. They don't travel in a pattern. They travel in a without parading. They used to move over it. Why it is so? It is because of the concept of resonance. Now, at that time, I know 90% of the students have not understood that example. Today, I will give you a practical example which you people have faced, but unknowingly you don't know what that is resonance. Let me tell you one example. Suppose you are having a very old motorcycle. Let us say that the fuel lead is somewhat loose. Okay. Now you will see that when you are traveling at 30 kilometers per hour, some sort of vibration noise is coming from that tank lead. Okay, fuel tank lead. Now you do one thing, you decrease the speed, the sound will move out, the noise will be vanished. Similarly, if you will increase the speed beyond this 30 kilometers per hour, you will see that the vibration is fading out. Now, if you will notice clearly that when you are actually traveling at 30 kilometers per hour, that noise is coming. Why? It is because at 30 kilometers per hour, the engine vibration is matching with the natural frequency of the fuel lead. That means everything has a natural frequency. You have a natural frequency, I have a natural frequency. Of course, our natural frequency is very complicated to find. Now, anything which is completely solid, that means you are using your mobile phone to study. That mobile phone as a whole is having a natural frequency. Now, what is this natural frequency? Natural frequency means the frequency at which the object, when vibrates, absorbs the maximum energy applied from the source. For example, at 30, actually the fuel lead is undergoing vibration of the engine starting from 0 kilometer till 100 kilometers. But at 30 kilometer, it is actually absorbing the maximum vibration energy from the engine. That is why when something means absorbs the maximum energy, it becomes very active and it starts oscillating in such a manner that it is going to create a lot of noise. So this is known as resonance. Now, since your electrical quantities are also oscillating quantities, okay, they are also moving in an oscillating manner, okay, in that case, this concept of resonance is also equally applicable to electrical stuff. Now, in suppose in a pendulum, it is moving, so that is a simple harmonic motion. Now, your AC signals are also harmonic in nature. So naturally, they are also undergoing your oscillations because I told you that one complete cycle starts from 0 degree till 365 degree. Again, the same waveform starts. So in this manner, this oscillation is taking place. So whenever there will be oscillation, there will be resonance. So resonance is nothing but when the applied frequency is matching with the natural frequency of the object, it used to absorb a lot of energy from the source. Now, let us see what is this use of this resonance. One simple example I am telling you. Suppose, let us say you people are listening to FM radio. So let us say our ITR is also having one radio, community radio center in Bhubaneswar. It is operating at 90.4. If you want, you can also see in the website. Those who are outside Bhubaneswar, they can also check it. So 90.4 megahertz is the frequency of SOA FM radio. And suppose you want to hear to this particular station, then what you have to do? You have to tune in your system in order to listen to it. Now, what is this tuning process? Or what is, or rather I will say, what is the use of this resonance? Why at all we are studying? Now already I have given a very bad picture of this resonance. So this vibration, this noise, all this thing. But the truth is that resonance is having a much better part. That means its picture is actually given in a wrong way. This resonance is utilized in a very beautiful manner in electronics and electrical equipments. Now let me show you one example. Suppose let us say that your radio you are tuning, your FM radio you are tuning. So once you want to tune to 90.4, then only you can listen to the music. But if you are tuning it nowadays, you are going for digital tuning. So let us say you will tune it to 90.2. You will listen to this FM in a very feeble manner, because it is not the natural frequency of the station, neither your applied signal of the radio is matching with this. So naturally the absorption of energy from the electromagnetic waves running at 90.4 megahertz is not matching, or is very close to it. That is why it is not absorbing the maximum energy from the signals. Now, if you will tune it to, let us say, 90.7 megahertz, then also it is not matching with this 90.4 megahertz. That is why, no doubt, it will catch some signal, but it will be filled with a lot of noise. Why is it so? Because it is not absorbing the maximum energy. Now, once you tune it perfectly to 90.4, the two frequencies matches. That means this is a resonant condition, and therefore your radio set is going to absorb maximum energy from the signals that is sent by our community radio center. And therefore, the amplification process in your radio will be much better, and therefore you can listen to the music in a nice way. So this is the main use of resonance. Particularly, similarly, in your television, you are tuning in the different channels. No doubt you are actually nowadays not tuning, because all these are digitalized. They are having microcontrollers which know the frequency band. It will automatically set the impedance of the circuit to that frequency. So that is a different issue. But long back, during when I was a young fellow, like a kid, during that time, actually, the television revolution came to India. Maybe in the 80s. I was born before 80s. So just remember, maybe I am up to your father says. You ask your father, they will tell you. They used to have televisions where you have a channel selector and you have to rotate it, and all of a sudden the video and the audio will be audible to you. Now that is known as tuning. And tuning is nothing but adjusting the frequency to go for a resonant frequency. So I have given you all the picture of this resonance. I have told you understand what is this resonance in electrical terms. Okay. So resonance electrically are of two types. One is a series resonance, the other one is a parallel resonance. Now, since parallel circuit, RLC circuit is not there in your course, so we will not discuss about that. We will only concentrate on series electrical resonance. Okay. So as you can see, the definition of resonance is already given. Electrical series resonance is a condition which occurs at a particular frequency where the circuit impedance is minimum, and therefore the current in the series RLC circuit is maximum. That means when the current is maximum, the series RLC circuit is going to absorb the maximum amount of energy. Got it? Now that particular frequency where the series resonance is taking place is known as resonant frequency. Now let us try to derive it mathematically. Now don't look at these derivations, just look what I am saying. Now we all know that your Z is given by V by I. Okay, or as I told you, in case of resonance, the maximum energy is going to be absorbed. Now we know that max P, the energy is equal to I square R. Let us say it is equal to I square R. That means R is a fixed quantity. So if I could increase the value of this I, then only the power absorbed will be maximum. Now what is I? I is nothing but it is equal to V by Z. Okay, it is equal to V by Z. Now what is Z? Z is equal to R square plus omega L minus 1 by omega ski a whole square root over. Okay. Now I will be maximum when your Z is minimum. So when Z will be minimum, let us see. Now R is a constant, L is a constant, C is a constant. The only variable that I have in my hand is the frequency of the supply system. Okay. Now Omega is nothing but the angular frequency, which is equivalent to this electrical frequency f. That means somehow, if I could tune the system in such a way that your omega L is equal to 1 by omega c, then this entire term becomes 0. So if it becomes 0, then the value of this Z is minimum and it is equal to R. Okay, so let us try to find out at what frequency this omega L is equal to 1 by omega c. For that, let us do this calculation. So modulus of omega 0. Okay, what is this omega 0? Let us consider that the resonant frequency is omega 0. So at omega 0, this term omega 0 L minus 1 by omega 0 c is going to be 0. So let us do one thing. Let us forget about this modulus sign and take this one onto the right hand side. If I am going to do that, I am going to get this equation. Now let us cross multiply. Omega 0 square is equal to 1 by LC, implies omega is equal to 1 by root over LC. But electrical people or the circuit branches people, other than mechanical and civil, they are always interested for frequency, not angular frequency. So let us do one thing. Instead of this omega 0, let us write it as 2 pi f0. So 2 pi f0 is equal to 1 by root over LC, or the resonant frequency f0 is equal to 1 by 2 pi root over LC. So if I know the value of the pure inductor, if I know the value of the pure capacitor, I can also find the resonant frequency for tuning purpose. Okay, so this is the last thing, that is the variation of Z and I with angular frequency. So usually we write it on a logarithm table because logarithm tables are based on powers. So a very long range can be condensed down to a very small diagram. So that is why we have used a logarithm scale. So Z is minimum, okay, note, Z is minimum at resonance. So let us say this is the resonance frequency omega 0. So you see Z is going to be minimum over here. Similarly, if Z is minimum, I is definitely going to be maximum. So you can see the maximum value of I occurs at omega 0. And the best thing is that at resonance, the power factor is 1. Because your Z minimum is equal to R. So it becomes a purely resistive circuit. So at resonance frequency or at resonating condition, the impedance of the circuit or the entire circuit becomes a purely resistive circuit. So with this, we come to the end of this chapter, and this is also my last class. So 26th we are having your exam. So I'll try my best. Okay, I have already shared the slides for this this video for this chapter number 32. You can check it for yourself. And secondly, if you are having any sort of doubt, please do message me on your WhatsApp group. And if you have any problem, I'll solve it in pen and paper and just dispatch you over the WhatsApp. So that is not at all going to be an issue nowadays. So I hope you people will be doing very brightly in the exam. Anything else you want to tell? Yes, anyone? 30. Oh, chapter 30 also I have. Okay, I will do it. Okay, just do it. I will do it right now because I have a very poor memory, so I may forget. Just be over here. Please confirm me whether you have received your emails or not. You all will receive a mail from Electroholic. That is my personal email ID, electroholic@gmail.com.